now we have our own discrete Fourier transform code, which is basically just this one line. It's basically doing a matrix vector multiplication. This vector is multiplying with this matrix. But still, it's a Fourier transform. It's our own discrete time Fourier transform code, right? And let's try to compare it with the Matlab DTFT code. And this DTFT code is called fast Fourier transform. And if you haven't used the Matlab fast Fourier transform code before, you can type help in the command window. Type help Fft, and then it's gonna display the help page for the discrete Fourier transform. You see, Fft for what? For discrete Fourier transform, right? Fftx is a discrete Fourier transform, DFT of vector x, right? Um, so the reason that I call my code a discrete time Fourier transform is because we are sort of assuming that the horizontal axis of the signal is time, right? But it doesn't have to be. It could be, for example, depth, right? If you are a geophysicist, you are looking down towards to the interior of the Earth, so the vertical axis, so the horizontal axis could be depth, right? If you are an atmospheric scientist, you are looking up, so the horizontal axis could be the elevation or altitude, right? That kind of thing. So it doesn't have to be time, right? And in that case, we just call our transform discrete Fourier transform instead of discrete time Fourier transform, right? So there are different kinds of interpretations of the horizontal axis in different kind of discipline, but in principle, they are all just a discrete Fourier transform, right? So we can just call it DFT or instead of DTFT. So we can just call it DFT basically. And how to actually use the Fft code? You basically give it a vector, and then it's gonna return another vector. And usually this return vector is a complex sequence, and basically it's actually doing this kind of summation, right? And the formula that you can you can compare this formula with our formula here, right? With our formula here, it's actually the same. It's actually the same. Maybe the notation is a little bit off, right? K subtractor one and subtractor one is gonna, but in practice it's basically identical, right? So now let's write some codes, and we're still gonna use the same example, right? But instead of using our own DFT code, we're gonna call Matlab's Fft function to do our transform. So maybe I should just add another section, right? So if I just so I have the input signal here. That's x, right? That's x. I still have it in my memory. So if I want to do a xf equals to Fft x, and then that's gonna accomplish the Fourier transform of x by using the Matlab Fft function. But you will see that this xf will look actually very different, quite different from the Fourier transform that we have obtained here, which is represented as big X, right? But let's maybe let's look at the figures, right? So here's the here's the Fourier transform, the magnitude, angle, phase angle, real part, imaginary part generated by using our own Fourier transform using this line basically, right? Here I'm actually calling the Matlab Fft function. So let's give it a try. Let's give it a try, and then let's make another plot. Maybe let's just plot the amplitude of xf, the magnitude of xf. ABS, right? Xf. You sort of see if you compare this magnitude with this magnitude, it looks quite different, right? It actually looks quite different. First of all, for the Matlab Fft function, it has just like 5 points on it. 1, 2, 3, 4, 5. Exactly the same number of points as the input sequence, right? How many points we have for x? We have 5 points, right? 5 points defined here, right? And then the Matlab Fft is going to produce an output that also has just 5 points. Just 5 points, right? Second of all, you can sort of see the pattern, even though the trend looks quite similar, right? So if you compare this figure with this figure, the trend looks quite similar, right? But they are not exactly the same actually. And for this particular plot, you don't really see the last point going up, right? But here you can sort of see the last point actually is going up, right? So the trend is actually a little bit different. I'll tell you why. I'll tell you why in a little bit. The Matlab Fft function actually is not just doing 0 to pi. In our own code, our transform is limited to the frequency range that goes from 0 to pi. So if you look at the range of W, right, it's pi divided by big M times K. K goes from 0 to big M, right? So when K equals to 0, W equals to 0. W is our omega, basically. It's our omega. That's our angular frequency. And then when K equals to big M, W equals to pi. So basically our frequency range goes from 0 to pi. What I can tell you is that for the Matlab Fft function, it's not going from 0 to pi. It's actually going from 0 to 2 pi, or from minus pi to positive pi. So it's actually doing a transform on a frequency interval that's like twice as large as our own code. So in fact, the last 2 points in the Matlab Fft output is actually for pi to 2 pi, right? And if you actually use an Fft shift function, so if you help Fft shift allows you to actually shift, you can sort of say shift the 0 frequency component to center of the spectrum. So if I instead of plot just the ABS XF, if I do Ft shift XF, I'm gonna plot the absolute value or amplitude of the Fft shifted Fourier transform, right? Then you'll see that it's actually symmetric, right? It's actually symmetric. But the horizontal axis is no longer 0 to pi anymore. It's actually from minus pi to positive pi. Here I did not specify what the horizontal axis actually is, but this plot is supposed to give 0 frequency at the center, right? So here it's supposed to be the 0 frequency, and then this is the negative frequency, and this is positive frequency this side, right? So that's the output of the Matlab Fft function. So you have to be careful about how it is how the output is organized. So if you do not use Fft shift, if you get rid of Fft shift, it's basically placing the negative frequency on the end of the transformed sequence, right? And then if you do an Fft shift, it's gonna take the negative frequency part to the beginning of the sequence and make 0 frequency sort of in the center of the output sequence, right? So that's one of the things that you have to be careful. But why the output has just so few points, right? The number of points is kind of fixed by the number of points used in your input, right? But can you actually make it denser, for example? Can you actually make it denser? Yes, I can. I can actually make the output very dense in frequency domain. And the way for doing that is to pad the zeros in the time domain. So if I define x1 equals to zeros, so instead of using 500 points, I use 1000 points. So m times 2, this many rows, and then 1 column, for example, right? And then that's my x1. And then x1, 1 to the length of x equals to x. So basically, I'm padding zeros behind x, and this new vector is called x1. You see, so for the first few points, for the first 5 points, basically, x1 actually equals to x, and then x1 just equals to 0, right? After the first 5 points, it's just all 0, and then my xf has to be the Fft of x1, right? And then if I execute this, now if I make a plot, you can sort of see it's a lot more smoother, right? And if I just plot the positive frequency part, And if you compare this magnitude with this magnitude plot, they look a lot similar, right? It's actually a lot similar, right? So you can basically duplicate them. You can plot this new line on top of this line by just sort of do an overlap plot. So if I want to go back to the subplot 221 and then hold on to the old plot, right? And then I can just plot what was k divided by big M, right? And then ABS XF want the length of big X. But let's use a different color, right? So we can see the two lines. Maybe use a dash line, right? And then now let's figure 1. And you can sort of see now the red line, red dash line, which is our Fourier transform generated using the Matlab Fft function, right? It's right on top of the blue line, which was generated by using our own FFT DFT code, right? It's one-liner, right? They are exactly the same, actually, right? Exactly the same. So what does it tell us? What does this experiment actually tell us, right? If we don't do this kind of zero padding, the output XF is just gonna have like 5 points. But if we pad zeros, if we pad enough zeros after the input sequence X, then the Matlab FFT function is gonna give us a much denser sampling in the frequency domain, right? So basically padding 0 in the time domain after the sequence is gonna densify the sampling in the frequency domain if we are using Matlab FFT function, right? So that's one of the things that we can observe right away from this particular example, right? And another thing that we have to be careful is that the Matlab FFT function is actually not just doing a transform in 0 to pi. It's actually doing a transform from 0 to 2 pi, basically. So the frequency domain output actually goes from 0 to 2 pi. That's something that we have to remember. Or from minus pi to positive pi. But the minus frequency part actually goes to the back of the output sequence. The second half of the output sequence. You have to sort of shift it using a Fft Shift Function to shift the negative frequency to the beginning of the sequence, so that zero frequency is actually at the center, right? So that's another thing that we can learn from this particular example, right? But if we actually sort of compare the phase angle, or the real part and the imaginary part of the output sequence XF with the big X, we're gonna see they are still different. Even though the magnitude is identical, but the phase is actually different, and the real part and the imaginary part are also different. So let's still open another window, right? Let's open another figure window, right? And then this time let's plot the angles, right? Let's plot the angles. So how did I plot the angle for? I did it here, right? Let me just copy it. So that's the angle generated by using my own FFT function, right? That's the angle of big X, basically, right? But now let's hold on to this plot, and then plot k divided by big M, and then let me get the angle of XF divided by pi, but using red color. Oh, sorry, the length is not the same. Want to length of big X, right? So you don't see the angle sort of on top of each other. The angles are different, actually. The phase angles are different. Right? And if you look at the real and the imaginary parts, they are also different. So I plotted the real part here. That's the real part of my big X, right? And then if I hold on to it, and then plot k divided by M, if I plot the real part, you can sort of see they are also different, right? The same is also true for the imaginary part actually. The imaginary part are also different. So why they are actually different, right? Why they are different? The reason that's different is because of the horizontal axis actually. The horizontal axis for the input signal here it's goes from like a -1 to 3, right? That's the horizontal axis for our input x, the time domain signal, right? And then when we did the Fourier transform, on this one line, we actually used m, the horizontal axis, when we sort of try to compute the big W matrix, right? So the horizontal axis is actually has been taken into account in our own Fourier transform code, right? But when we actually did the Matlab FFT code, when we called the Matlab FFT code, it's actually not utilizing the horizontal axis of the input function, right? If you actually look at the help page of the Matlab FFT function, how do you actually use it? Here x is the input signal, right? Big N, it's sort of the endpoint FFT padding zeros, right? And for all those options, you don't find an option that allows you to input a horizontal axis for the input time domain signal, right? And the reason that Matlab actually is doing that is because it's basically assuming the horizontal axis of the input signal starts from point 0. So it's actually assuming here it's actually assuming that this x1 has a horizontal axis that starts from time 0, right? And the output is actually for the output of the signal that's actually a shifted version of this particular input that we're actually using in our own codes, right? If you actually imagine that you can basically shift our input signal to the right by 1 unit in order for the horizontal axis to start from 0, right? Because now the horizontal axis starts from -1, right? It starts from -1. So how do we actually make the Matlab FFT function output a sequence that's the Fourier transform of a shifted version of this input sequence, right? And we have to sort of look at this particular formula. It's called time shifting. It's one of the properties of DFT, basically. It's one of the properties. Later on, we're going to look at why this formula is actually correct, right? But now let's look at what it actually telling us, right? So the Fourier transform of a shifted input signal. Here it's the x signal that's being shifted to the right by k units, right? The Fourier transform of this shifted version of the input signal actually equals to the Fourier transform of the original sequence xn times e to the minus j omega times k. K is the amount of shift, right? So let's try to incorporate that into our example here. Let's try to incorporate this formula into our example here. It means what? It means that in order to get a Fourier transform of a sequence that's not starting from 0, starting from -1, you have to multiply the output sequence of FFT XF with this complex number, this complex sequence. You see? So what exactly is this? It's basically a complex exponential, right? And then k is the amount of the shift. What's actually our amount of shift, right? The amount of shift for us is basically -1, right? Because it's not starting from 0, it's starting from -1. So what we have to do is to multiply xf. Of course, it has to be a dot multiply. It has to be a dot multiply. So xf, let's define xf1. xf1 equals to xf1 to the length of big X dot multiply. Dot multiply this complex exponential. So it's -1i, j is the imaginary unit, 1i, times the frequency, right? So what's our frequency axis? Frequency axis is W. We have defined our frequency axis here. It's W, right? So we have to multiply with W. And then times the amount of shift, which is -1. Right? And let's see if this code actually works. It was saying the dimension must agree, right? Because W is actually a row vector, but here it's actually a column vector. So maybe I should transpose it. Or maybe I should transpose this one. I'll transpose this one. Now it works, right? So now let's compare the phase of xf1 with the phase of big X, right? So subplot 2, 2, 2. Hold on, and then plot k divided by big M, and then the angle of xf1 divided by pi, right? Still, let's use red dash lines. Right? And then let's just give it a try. Let's just give it a try. Let me close this figure. Let's, so it actually looks like it's not really giving me the correct result. So if we go back to check what might be wrong, it's actually here. I'm not supposed to transpose the first one. The Matlab transpose actually is going to conjugate the vector. So because it's a complex vector, right? So still I have to transpose the second vector. I have to put the transpose on W because W is actually a real number. Um, so that's something that we have to be careful about. So what it's actually telling me is that if I actually transpose a complex sequence, for example, if I have a 1i and then 2i, 3i, that's my complex sequence, right? But if I transpose it, you see, the Matlab transpose function prime on a complex vector, on a complex sequence, not just sort of converting a column vector to a row vector here. It's also changed the sign. It also changes the sign of that complex vector. Basically, it's actually conjugating. It's conjugating the complex numbers in those complex sequence. So if I put the transpose, if I put transpose here, then it's not just gonna sort of convert it into a row vector. It's also gonna conjugate all the complex numbers inside of this vector, right? And then it's not gonna give me the correct result. It's gonna give me this dash line, right? It's not the same as. But if you actually put the conjugation on the W, on the frequency, it's a real number. It's a real sequence, right? It's just gonna convert the column vector, row vector to a column vector. So if you do that, it's gonna work, right? It's gonna work. And then if you actually plot it, so this particular figure is like not so good now. Let's you have too many lines on it. So subplot 2, 2, 2, right? Let's hold off, and then let me replot this. Let me just replot this one. So that's the phase angle of my big X sequence, right? And then now let's plot the phase angle of our complex sequence, of our FFT sequence. Now they are actually exactly the same, right? And you can also compare the real and imaginary parts. Again, hold on. Now, real XF1. And then subplot 2 to 4. Hold on. Plot. Okay, big M XF1. Right. Now they are actually exactly the same. Right. So here we actually used what? We actually used the time shifting property of the DTFT, or a discrete Fourier transform. The Fourier transform of a time shifted version of the signal actually equals to the Fourier transform of the original signal before the shifting times this complex sequence, which is basically e to the minus j omega times the amount of the shift, right? So we haven't talked about the properties of DFT yet, right? This is one of those properties. We're going to look at the other properties in a little bit, right? But here we actually have used one of those properties, and it shows you that how you can actually account for a non-zero starting time, in your input sequence in the Matlab FFT function, right? The Matlab FFT function itself doesn't really account for that. It assumes that the input sequence actually starts from time zero, right? But you, the user of FFT, can actually account for a non-zero starting time by multiplying with a complex sequence that looks like that, right? E to the minus j omega times the amount of shift, right? The amount of shift. And then the result is going to be exactly the same as produced by this formula, right? So that's the second part of our DFT example, right? And now let's look at the properties of DFT in more detail. Let's try to look at those properties in more detail, right? So now let's try to verify this linearity property, right? So here I have defined two signals, basically n1, that's the horizontal axis of the first signal, goes from -1 to 3, and then x1 goes from 1 to 5, right? And then we have a coefficient alpha equals to 2 for the first signal, right? And then xx1 is basically the scaled version of x1, right? It's alpha times x1. And then I do the same thing for the second signal. The second signal goes from 0 to 6, and then the amplitude goes from -5 to 1. And then the coefficient I'm going to multiply beta actually is equal to 3. And then xx2 is basically a scaled version of x2. It's just the x2 times this scalar, right? And then I have to construct a composite signal, which is this thing under the selection, alpha times x1 plus beta times x2. And then to do that, I use sig add, right? Because the two axes, the horizontal axis of the two signals are different. So xx1 with its horizontal axis n1, and then xx2 with its horizontal axis that's n2. And then the result goes to xx3 and n3, right? Now I can start to do my Fourier transform. I'm gonna use the same kind of horizontal the frequency axis as I was using in the previous example, right? In the previous example, I was using this horizontal axis for frequency omega, right? 501 samples, k goes from 0 to m, big M, and then that's my frequency omega, w basically, w, right? I'm using basically the same horizontal axis, so w still goes from 0 to pi. Then I do my Fourier transform for x1, right? That's my formula. It's basically the same equation, the same code that I used for computing this line, right? It's still the same. It's just I'm replacing x with x1 and n with n1 basically. So here I'm actually computing the Fourier transform of x1, right? Here it's n1 and then x1, and then I do the same thing for x2. Here I'm doing the Fourier transform for x2. So that's the signal itself. That's the horizontal axis, right? And then I have to do so that's the Fourier transform of x1 and the Fourier transform of x2. Basically it's this part of the formula, right? So big x1 actually equals to big F x1n, right? Fourier transform of x1, and then big x2 actually equals to the Fourier transform of the second signal x2, right? And then I have x3. x3 is what? It's xx3. That's basically the addition of the two scaled signals, right? xx3 with its horizontal axis, that's n3. So that goes into big x3. Big x3 is Fourier transform of the whole thing, right? So x3 actually is equal to the whole stuff that's under the selection, right? Right. That's x3. right? And then what I have to do is to compare big X3 with this line, which is XX3. XX3 is actually the scaled version of X1 plus the scaled version of X2. So it's basically X1 times alpha, which is basically this thing times alpha, right? And then X2 times beta, which is basically this thing times beta, right? So what I have to do is to compare X3 with XX3, right? So 4, 1, 4, right? Suppose we plot the amplitude. We plot the amplitude ABS, right? ABS, maybe K divided by big M, and then ABS X3. Hold on to it, and then plot ABS XX3, right? Let's just compare the amplitude first. Dash dash, right? And let's give it a try and see if they are identical, right? And you can sort of see they are indeed identical, exactly the same basically. So the amplitude is actually exactly the same, right? And then now let's compare the phase, right? Let's compare the phase. Let's do the angle. If both the amplitude and the angle are identical, then the two signals are identical, right? Let's replot it. And you can sort of see the angle are also identical, you see. So it means that the linearity is exactly the same. So maybe we should just not use 4, but use 5. Let's use 5 subplots. This one plots the ABS, right? And then the next one plots the phase. The phase angle, basically. That's right. So let's rerun it. Right. So the amplitude is identical, phase is identical also, right? So that basically is a validation of the linearity of the two signals, right? And then now let's look at the second property, which is the time shifting, right? So the time shifting, we already looked at the we already validated this time shifting by using the Matlab Fft function call, right? In our previous example, so basically here we are actually comparing the Matlab Fft output xf, but we are multiplying with the exponential e to the minus j omega k, e to the minus j omega k. K is the amount of shift, right? Here it's -1. So we have validated this time shifting property in our previous example, right? But let's look at mathematically how it works out, right? So the Fourier transform of a shifted signal, right? So all we have to do is to, again, by using the definition of the Fourier transform, right here. That's the definition of the Fourier transform. So what we have to do is to replace xn with xn subtract k here. Replace xn with xn subtract k, right? So replace xn with xn subtract k, right? And then what we have to do is to find a substitution. So using n subtract k and substitute n subtract k using n prime. So we define a new variable n prime. N prime actually equals to n subtract k, right? So now we can replace xn subtract k with xn prime, right? And then n. So if n prime equals to n subtract k, then n equals to n prime plus k, right? So here I'm actually replacing n with n prime plus k. And then the summation index n goes from minus infinity to positive infinity, right? So n prime still goes from minus infinity to positive infinity, you see. And then we can sort of write this exponent into like two components, this part and then this part, right? And you can sort of see only this part actually depends upon n prime. This part doesn't depend on n prime. So e to the minus j omega k can be taken out of the summation. E to the minus j omega k you can move it out of the summation. And then the stuff that's inside of the summation is basically xn prime e to the minus j omega n prime. And n prime is the summation index, right? Because it's n prime is the summation index, you can sort of replace it with whatever letters that you want to use, right? Here we replace it with n prime, but this n prime doesn't have to be equal to n prime that we used to substitute n subtract k here, right? It doesn't have to be. You can just replace n prime with any letter. You can just replace n prime with l or k, or it doesn't really matter, right? But you can sort of see this particular formula becomes identical to our definition of the Fourier transform of xn, right? Basically, that's the stuff that's inside of the square bracket equals to the Fourier transform of xn, the signal without the shift, the original signal. And now you can sort of see that this formula is actually valid. So the Fourier transform of a shifted signal equals to the Fourier transform of the original signal without the shift times e to the minus j omega k, and k is the amount of the shift, right? So that's sort of the time shifting property of Fourier transform, right? And now let's look at another property, which is the frequency shifting property. So this is basically telling you that if you wanna sort of if you do the Fourier transform of the input signal xn, multiply with e to the j omega 0 n, and omega 0 is some sort of constant frequency that you have selected, right? The Fourier transform of this thing actually equals to what? It equals to the Fourier transform of the original signal, but it has been shifted. You see, it has been shifted to the right by a certain amount. That's called omega. That's omega 0. That's the frequency that you have selected, right? You can sort of understand this particular formula by so the important thing is to realize that in the frequency domain, it's a function of omega, right? And this side of the equation, x e to the j omega subtract omega 0 actually means what? Actually means a shifted version of this big X function, which is a function of omega, right? So if you multiply the input signal with e to the j omega 0 n in the time domain, and then in the frequency domain, it's equivalent to shifting the Fourier transform of xn by omega 0, this amount, to the right, right? So to understand this particular formula, let's look at its derivation, right? So the Fourier transform of xn times e to the j omega 0 n, right? So what you have to do is to in the Fourier transform formula, what you have to do is to replace xn with xn times e to the j omega 0 n, and then the rest of the Fourier transform formula, basically e to the minus j omega n, right? Now you can do some manipulations now. So xn, you can combine these two last exponentials, complex exponential functions together, becomes minus j omega subtract omega 0 n. You see. Now you can introduce another sort of variable that's called omega prime. You can use omega prime to replace omega subtract omega 0. So omega prime equals to omega subtract omega 0, right? And then if you compare this particular formula with the original formula for Fourier transform, you'll see right away that this actually equals to big X e to the j omega prime, right? And at this point, you can replace omega prime with omega subtract omega 0 again, right? So it becomes x e to the j omega subtract omega 0, right? So that has proved this particular formula. But let's look at this, what this formula actually means in Matlab. Now let's look at how we can validate this frequency shifting property in Matlab, right? And this frequency shifting is also called modulation, actually. So this kind of technique is actually used quite often in electromagnetic waves, in transmitting electromagnetic waves. In fact, if you are listening to uh, radio, they actually transmit those kind of electromagnetic signals using modulation. So different kind of channels are modulated to a different frequency band, and then combined together with other sort of channels together, and then sort of push it to you or propagate it to your radio receiver. So, and then the radio receiver is going to demodulate it. It's going to separate the different channels into like a different frequency bands, and then um, convert it into the sound that you can actually hear. All right. So it's a modulation technique is used quite often to combine different signals together before propagating them, and then demodulation is applied on the receiver end to actually separate different signals that has been combined together. So let's look at what's going to happen in this particular example, right? So here I'm actually trying to construct a input signal x. So here x is actually a cosine function with a frequency that's 0.2. So if you want to make a plot of this particular signal, let me uncomment this line. Right, you can evaluate this selection. You can sort of see it's a cosine signal, right, with some kind of oscillation, right? And that's basically our input signal, right? Now let's modulate it. So let's modulate it by multiplying x with some kind of exponential function here, right? Either j omega 0 n. And omega 0 that we have picked, the value that we have picked is pi over 2. It's half a pi over 2. And then j is 1i here, right? N is n, right? That's our modulated signal, x1, the signal after modulation, right? And then let's try to construct our horizontal axis. This time we're constructing not just the positive side of the frequency, we're also constructing the negative side of the frequency. So still big M equals to 500, right? But k goes from minus m to m, right? And then frequency actually equals to pi divided by m times k. So when k equals to minus big M, W equals to minus pi. And when k equals to big M, W equals to pi. So the frequency range is going from minus pi to positive pi here, right? Now we can construct our Fourier transform. We can do our Fourier transform. So big X is going to be the Fourier transform of the signal without the modulation. So it's just going to be X. And then the rest of the formula is exactly the same as before, right? The code is exactly the same as what we have used before, right? And then x1, big x1 is going to be the Fourier transform of the modulated signal, x1. That's the x1 is the modulated signal, you see. So x1, the input signal now becomes x1, and then the rest of the formula is exactly the same as before also, right? So that's the Fourier transform of the modulated signal, right? So if you want to take a look at this these two signals, let's plot them. Let me cut it and then paste it here, and do a hold on here, right? And now let's just plot the absolute value, the magnitude, right? And then the horizontal axis still goes from like -1 to +1. So the blue curve that's plotted here, it's the absolute value, the magnitude of the original signal. And then the red line, the red curve, is the amplitude of the Fourier transform of the modulated signal x1. x1 is here, you see. That's the Fourier transform of the modulated signal x1, right? And you can sort of see their shape. The shape are identical, but the red curve, the Fourier transform of the modulated signal, has a different location. So the horizontal axis is a normalized frequency now. So it goes from -1 to +1, right? And you can sort of see the location. So here it's 0, right? 0 frequency. That's the original signal. Right? It's basically a symmetric signal. If you look at the amplitude, the magnitude, it's symmetric, right? And then the amount of modulation that we applied here is pi over 2, right? Pi over 2. So if you normalize pi over 2 by pi, then it's 0.5. So you can sort of see 0 has been shifted to pi here. See? So let's try to shift the Fourier transform of the original signal without the modulation. That's big X, right? And then let's just use the sig shift. Let's use the sig shift as our to shift the Fourier transform of the original signal without the modulation, right? So the input is X, right? The horizontal axis is W. That's our frequency, right? And then the amount of the shift is pi over 2, right? That's the frequency that we used for modulation here. It's pi over 2. So we shift the horizontal axis, shift the Fourier transform by pi over 2. And then the output goes into xx1 and f1. F1 is the horizontal axis of xx1, right? So now let's make a plot of the magnitude of xx1, but its horizontal axis is f1, right? F1 is actually goes from minus pi to positive pi. So you have to sort of normalize it by dividing pi. And then we are plotting them in black line, plotting the magnitude in black, right? And then let's try to execute these two lines. These 3 lines actually. And then let's take a look. And you can sort of see the black line is right on top of the red line, right? So the shifted big X actually is right on top of the Fourier transform of the modulated signal. Right, here we are actually plotting the magnitude of x1, the Fourier transform of the modulated input signal in red, right? And now here black is right on top of the red, means that they are identical, right? So the Fourier transform of a modulated input signal equals to the Fourier transform of the original signal shifted by the amount of the frequency that you used for modulation. You see? And it's also a very important property that we're going to revisit when we deal with the sampling theorem, right? How do we actually sample the signal in time and frequency domain? So that's modulation or frequency shifting. Now let's look at another property of discrete Fourier transform, which is the conjugation property. Right, and then we have to be careful about this particular formula here, because conjugation might be an operation that you are not exactly very familiar with at this point yet, right? But let's try to understand it still. Let's try to understand it. So here's the input signal now becomes what? Becomes the conjugation of the original signal, right? So star means conjugation. So if X is actually a complex time domain signal, conjugating it means that you are just reversing the sign of the imaginary part of that complex signal xn, right? And if you do a Fourier transform on the conjugate of the input signal, what's gonna be the output of that Fourier transform, right? The output of that Fourier transform is this. This means what? There are 2 differences that we have to pay attention to. One is this star, right? It means conjugation here. And then what's actually the stuff that's inside of this parenthesis? It's e to the minus j omega n. There's a minus sign here, right? If you compare it with the original Fourier transform formula, it's big X e to the j omega, right? So what exactly is big X e to the minus j omega? It actually means you are reversing the horizontal axis of big X. So big X e to the minus j omega actually is a folded version of big X e to the j omega. So 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 what this so so this formula looks simple, right? But it actually has two operations that's embedded in it. One is this minus sign, which actually means a folding in the frequency domain. So you're basically folding big X e to the j omega, and then you are taking a complex conjugate of big X. Taking a complex conjugate is basically a operation on the imaginary part of big X, right? So the Fourier transform of the conjugated input actually equals to the conjugate of the folded version of the Fourier transform of the original signal, right? It looks really complicated, right? Because to explain it, you have to sort of like introduce two operations. One is a folding, and then the other one is a conjugation, right? But let's try to understand it from the math, right? So the Fourier transform of x star n. So what you have to do here is to replace x with x star now, and then the rest of the formula is exactly the same as before. So it's still e to the minus j omega n. N goes from minus infinity to positive infinity. The only thing that has been changed is here. We're replacing xn with x star n, basically, right? That's the definition of the Fourier transform, basically, right? And then, if you are not exactly familiar with the operation of complex conjugation, what you have to do is to sort of understand sort of what's actually happening here. So here I'm actually so the conjugate of x actually means that I'm reversing the sign of the imaginary parts on x, right? And what I can tell you is that this formula actually equals to this formula. So so conjugate if you actually conjugate suppose you take this conjugation inside of this summation formula, you put this conjugation on xn, then what you can recover is x star n. And then if you put this conjugation onto this thing, onto e to the minus j omega n star, this star and this star is going to cancel out. So a star actually just means reversing the sign of the imaginary part, right? But if you actually apply the star twice, you're basically switching you're basically just canceling out this operation of reversing the sign of the imaginary part. So this star is going to come down to xn, and then this star is going to cancel out this n, and then you can sort of validate that this equation, the whole thing here, actually equals to the whole thing here. Right? If you don't believe me, you can sort of try a few numbers, right? So if you just use a single complex number, suppose 1 plus 2i, take the conjugate of it, means 1 subtract 2i, right? And then if you conjugate it again, it's 1 plus 2i, you recover the old number, right? So now we come down to this particular equality. How do we actually validate this equality, right? So the conjugation of e to the minus j omega n actually equals to e to the j omega n. So if you don't believe me, you can expand this e to the minus j omega n using the Euler's formula. So e to the minus j omega n actually equals to cosine omega n subtract I sine omega n, right? And then if you actually reverse the sign of the imaginary part, it's plus sine I plus I sine omega n, right? And that equals to e to the j omega n, right? So it's basically the conjugation of this whole thing. And this whole thing actually equals to what? So if you introduce a minus sign here on omega, introduce a minus sign on omega, and then you have to cancel out the minus sign by using another minus sign, right? Right. And then if you compare this formula with the original definition of Fourier transform, this whole thing that's inside of this square bracket actually equals to big X e to the minus j omega. Do you see it? Do you see this? This thing actually, if you replace minus omega with omega prime, for example, omega prime, and then the stuff that's inside of the square bracket is exactly big X e to the j omega prime. And then omega prime equals to minus omega, right? So the stuff that's inside the square bracket becomes big X e to the minus j omega. It's a folded version of big X, right? And then you still have this star, the conjugation outside of the square bracket. So you move that star onto big X, right? So you recover this formula, right? And that's conjugation. But let's see if we can actually validate it in Matlab. So here, let's try to validate it, right, using Matlab. So here I'm trying to generate a complex time domain signal. So the horizontal axis goes from like -1 to 3. So that's the horizontal axis. And then that's my time domain signal, right? So it has a real part. It's a random sequence, 5 numbers, 1 row, 5 columns, right? Plus, and then that's the imaginary part. So in Matlab, 1i means just the imaginary unit times another sequence of random numbers, right? 5 rows, 1 column. That's my input signal, right? And then I have to generate the conjugation of it, x1. x1 is just the conjugate of x. And then in Matlab, if you want to take a conjugation of a complex sequence, there's a function that's called conj. Right? If you haven't used conj before, you can type help conj. Right? It's telling you that it's a complex conjugate. The conjx is a complex conjugate of big X. For complex x, conjx equals to real part of x subtract I times imaginary part of x. You see, so it's basically reversing the sign of the imaginary part, right? And we can take a look at it. Let's just subplot 3 rows, 2 columns, and then the first one, and then I'm gonna do a stem n, and then the real part of x, right? And then subplot 3, 2, 2 stem n imaginary part of x, right? And then subplot 3, 2, 3. That's gonna be the stem n real part of x1, right? That's the conjugated signal. And then subplot 3, 2, 4 stem n the imaginary part of x1, right? So if we just want to execute it, and then we can go back to our signals to look at the signals, right? So that's the real part of x, that's the imaginary part of x, right? And then that's the real part of x1. It's exactly the same as x. And then that's the imaginary part of x1. And you can sort of see the sign is reversed, you see. The sign is actually reversed. Here it's all positive, and now here it's all negative. The sign is reversed, right? So that's our x and its conjugate. Here we denote it as x1, right? Now let's try to construct our Fourier transform, right? We're gonna define our horizontal axis in the frequency domain first. So big M is still 500. K goes from minus big M to positive big M, right? And then that's our frequency omega, right? So W goes from minus pi to pi, right? And then that's the Fourier transform of the original signal. Here it's x, right? And then the rest of the formula is exactly the same as before. And then that's x1. That's Fourier transform of x1, which is the conjugate of x. Right? So here it's x1 times the old formula that we're using, right? So what do we have to compare? What do we have to compare? Is compare x1 with what? X1 with what? Here it's so x1 is basically the Fourier transform of the conjugate of x. Conjugate of x is x1, right? And then the Fourier transform of x1 is big x1. So big x1 is basically the left-hand side of this formula. So we have to compare it with the right-hand side. What I was telling you, the right-hand side involves 2 operations. One is the folding to account for this minus sign. So here we're actually doing a sigfold, right? We're doing a sigfold. sigfold big XW. You see, because big X, that's the Fourier transform of the original sequence X, and then its horizontal axis is W, right? That's a sigfold. And then we're doing a conjugation. That's a Matlab conjugation function, right? And then the output goes into big X x1, big X x1. That's the right hand side, right? So conjugation here, right? And then folding, the folding operation, right? Folding operation here, right? And then we can try to compare it. We can compare it with the x1, right? And we can do that by looking at the real part and the imaginary part. So subplot 3, 2, 5. Let's just hold on, and then let's just plot w divided by pi, right? That's gonna be or k divided by big M, right? And then let's just do real part x1, right? That's gonna be blue or using black, right? And then plot k divided by big M, then the real part of xx1. That's just using red, right? Subplot 3, 2, 6. Hold on, let's plot k divided by big M, imaginary part x1, right? Then plot k divided by big M, imaginary part of x1, xx1. Let's use red, right? So now let's run this part. Let's run this part of the code, right? Let's run this part of the code. And you can sort of see they are actually the real part and our imaginary part are indeed identical, because you don't really see any black lines. You don't see any black lines here. So it means that the right line is right on top of the black line. We have a hold on here, right? We have a hold on here. So maybe I should just try to use dash line, so we can still see the black line in the back, right? So maybe let me just close this figure and then redo another figure. Maybe just re-executing this part of the code. Right. So here you can sort of see the black line that's kind of in the back, right? So that shows the conjugation property, right? The conjugation property. But suppose x actually is a real signal. It has no imaginary part. So x is actually a real signal. And then what's actually happening here, right? What's actually happening here? So if x is actually a real signal, then its conjugation is basically itself, right? So big F x star n actually equals to big F x n, right? Big F x n actually equals to big X e to the positive j omega, right? So if actually x is a real signal, then big X star e to the minus j omega actually equals to big X e to the j omega, right? Which means what? You basically have recovered this symmetry property, basically, right? Big X e to the minus j omega equals to X star e to the j omega. So if you actually take conjugation on both sides, it becomes big X star e to the minus j omega equals to big X e to the j omega, right? You basically recovered this symmetry property if the input signal is a real signal. It means what? The conjugation of the folded signal equals to the original signal, right? So that's if you actually try to understand it better, then it means that the real signal, the real part of the signal for transform is an even function of omega, right? Because that's the folded part. That's the folded part. So you have a folding here, right? You basically just reverse the horizontal axis, and the real part is identical, right? And then the odd part is anti-symmetric, right? Here it's a folding, right? It's folding. And then the imaginary part has a minus sign on it, and that's corresponding to the conjugation that you apply. Conjugation means reverse the sign of the imaginary part, right? So if the input signal is indeed a real signal, then you are basically recovering the symmetry property of the Fourier transform, right? And this conjugation property is actually related to that symmetry property that we have talked about in a previous lecture, right? And that's conjugation.